It's preferable that the walls stay solid because that gives you your optimal design as far as strength. Structural engineers love solid walls, but what often happens is walls don't get to stay solid. Big old holes are created in them for things like doors. And so when we have a structure like this where we do have a solid wall, we're going to simulate something like a big, like a 16-foot wide garage door or something. So in our house that we evaluated in the previous video, or the wall that we evaluated, we're going to take that same wall and we're going to assume that we've cut a big old hole out of it for a 16-foot wide garage door and see how that changes. When we look at the structure of this, we still have the same forces involved in our house that are trying to push our house over, but now we have to resist them a little bit differently. So here's our new structure now that we have a big door opening in it. And now we want to apply the same force on the top of the wall and see how that affects our structure. So if we have a 20,000 pound lateral force being exerted on our structure, like so, what's going to happen is that 20,000 pound force has to be resisted now by these diagonal braces. And you'll notice that the angle that these braces make with respect to the ground are quite a bit larger. These diagonal braces are quite a bit steeper. So we're gonna use this in our next analysis to see how the structure, or how the forces and this whole thing changes as a result of this 20,000 pound load. Now the 20,000 pound load that's applied up here, it's assumed to be distributed evenly between these two shear walls. So if this is 20,000 pounds up here, then that means this shear wall is responsible for 10,000 pounds, and this shear wall is responsible for 10,000 pounds. So really all we have to do is analyze one of these with a 10,000 pound load at the top to see how the whole system responds. So here's our structure now that we've drawn, and I've cut out of the middle of this 24-foot wide wall, I've cut out a 16-foot garage door. So now all we're left with is two 4-foot sections of wall on either side of the garage door that still have to resist the 20,000 pounds. However, that 20,000 pounds is assumed to be distributed evenly across these two shear walls. So really what I'm working with is, if I erase this part here, I'm really just interested in analyzing one of these shear walls with a 10,000 pound load and trying to find out how that affects the structure. So I'm going to label my points here, A, B, C, and D, and let's work around this. Actually, I think to keep consistent with the previous problem, A, B, C, and D, let's sum our moments about point A to find our reaction at D. So I have 10,000 pounds times 10 feet minus the reaction at D in the vertical direction times 4 feet. So that's going to be 100 divided by 4. dy is going to be 25 kips. Compare that with our previous example where with the full width of the wall we only had 8.33 kips. Here we've increased that quite a bit. So let me erase this 4 foot here so I don't get our drawing too busy. 25 kips. Okay, and I have a 4 foot width there. Similarly, our reaction at A is also going to be 25 kips in the downward direction because the sum of all of our forces in the y direction are equal to 0. Okay, using that, remember from last time, we didn't even need this this member right there because there was no force in it. Okay, so we know that up here we're going to have 10,000 pounds of compression, so 10 kips in compression. We also know here we're going to have 25 kips of compression because the vertical component of force in this member has to counteract 25 kips. That's the vertical reaction. And now let's find out what the force in this diagonal brace would be. Okay, so if we look at point A, we have a downward force from our reaction, that's 25 kips, and we have a diagonal force, FAC. Now, FAC, if we sum all of our forces in our y direction, assuming up and to the right is positive, then we know that negative 25 kips from our reaction in A plus the vertical component of FC, which will be 10 feet divided by 10.8, the length of that diagonal, times FAC is going to be equal to 0. So now when we solve that for FAC, we get .27 kips tension. $27,000 pounds of tension, and we have two of those tension ones, in this one and the one in the other shear wall. So compare that to our last problem, where we had diagonal bracing going the full length or the full width of the wall, compared to this now when we only have 4 feet of shear wall, and we can see how decreasing the amount of shear wall we have drastically increases the amount of tension in that cable. In fact, the closer these get together, the more this increases to where as you approach 0 in your width between the anchor points on your shear wall, as that distance approaches 0, this force approaches infinity, because there's just no way for it to resist that kind of tension. It all has to do with the inverse sine or the inverse cosine or the tangent of the geometry of this building. That's how it plays in with the trigonometry of it. So not only that, but when the wind is blowing, the closer these two get together, the more these reactions increase. Because remember, even though we have our force distributed over 2 separate shear walls, the distance is so close that our attachments to our foundation are quite a bit more. 25 kips compared to 8.33 kips in our previous example. So as the closer these get together, the more this approaches infinity as well. And that makes sense, because if this is approaching infinity, and since it's being countered by the tension in this cable, then as this approaches infinity, that the tension in that cable also has to approach infinity. So, this is something that's very often overlooked, even with engineers and designers, how the shear wall, the absence of shear wall in buildings dramatically increases the forces that building has to resist. That's why in hurricanes, often the first thing to go is the parts of the house that have the large openings in them, because they don't have as much resistance to shear as other parts of the house as well. So very valuable example there that not a lot of people grasp. Here's our house with our garage door again. And what I've done here, instead of adding diagonal members, cross bracing, what I've done is I've added some shear walls, some shear reinforcement to it. And so what this illustrates is the same exact thing structurally. These resist lateral movement, and they do so in a very similar way as cross bracing does. Because if we're going to apply a load laterally this way, the whole thing wants to rack towards the right. So in this sheet, which is commonly plywood, in this sheet, it gets loaded in multiple directions. Across this diagonal, this plywood is experiencing tension, but across this diagonal, the plywood is experiencing compression. And then at every other point within that plywood, it's either a combination of tension or compression, depending on where that point of the plywood is with respect to the geometry of the house and the direction the forces are being applied. And so as this force is being applied, what restrains this whole house is not just the stiffness of the shear panels, the plywood, but also the connections. Because if the force is being applied this way, then these two connection points are being pulled away from each other, and then these two connection points are being pushed towards each other. So if you push this so hard that connection gives, then this whole thing fails. And so what shear walls do is they attempt to distribute this load over the entire perimeter of the plywood. And the way they do it is by adding connections to the perimeter of the plywood like this. So now you can see that there are several connections around around the perimeter of these shear walls. What that does is that when the force is applied to the building, instead of only two connections being able to resist that, or two nails or screws or whatever being able to resist that force is distributed over, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 different screws or nails or whatever. And so that 20,000 pound force, if it's divided between 20 different connections, then each one of those connections only has to account for 1/20th of that force, or 1,000 pounds each. The more connections, the more ability you have to resist that strength. So remember, a building is only as strong as its weakest structural component. So if the connections if the connections are the weakest, that's what gives. If the inherent strength of the plywood or the sheathing material is the weakest, that's what gives. This will crumple or it'll tear inside, depending on how the forces are applied. If the anchors to the foundation are the weakest point, the building won't stay where it's supposed to. It'll move. The anchors will pull out of the concrete, or the foundation won't hold it. All of these different things have to be taken into account in the design and construction of a building, so that everything will work together to counteract the loads that are imposed on it.